Okay, good afternoon, and thank you to the organizers for the invitation. So as Eva said, this talk concerns diagnostic methods applied to understand the basic physics of thrusters, plasma thrusters. So I'll start by providing some information on where I work. It's a research lab of the French National Research Center, located in Orléans. And this research lab is called ICAR, and it's a lab which works a lot on combustion, atmospheric chemistry, high-speed flows, and also plasma propulsion. So in our team, we have a team director who is more senior than I am, but we're two researchers working on plasmas. So this research lab is well suited to my activities because it's the site of the National Thruster Facility for Electric Propulsion for Plasma Propulsion Research. And this is the plasma chamber where industry partners and also academic partners do basic physics studies on plasma propulsion concepts. So my presentation will deal with, first I'll situate the topic by discussing why I study microturbulence in particular in propulsion plasmas. And then I'll present the results, the implementations of two diagnostics, a coherent Thompson scattering diagnostic I developed some years ago and a newly developed incoherent Thompson scattering diagnostic. And I'll explain my strategies for taking advantage of the information that we now have from these tools to understand the basic physics of these plasma thrusters. So to start out, microturbulence, of course, is very familiar to people working in fusion. And so in this talk, I've tried to make the link between fusion research and what I'm doing. And typically concerns investigations of small-scale instabilities. And as you've seen, I think, probably it's been mentioned briefly in previous talks, but microturbulence and plasma turbulence in general is very important for fusion devices such as tokamaks and stellarators. And in Professor Burhan's talk, for example, I saw the mention of possibly turbulence being one of the reasons why you have this clipping of the ion heating. So this is something which is extremely interesting to me as well. Microturbulence, in the case of tokamaks, is driven by ion and electron temperature gradients, which create perturbations and eventually is implicated in anomalous transport. Now, the consequences, as I mentioned, for this anomalous transport affects the confinement time of these devices and also is one of the drivers for the sizing of machines like ITER, the presence of these small-scale fluctuations. So the fact that empirical scaling of the devices required is something which has been known for a long time. These are the expressions for the confinement time in the L mode and H mode operation. And you can see here it's just a lot of coefficients and raised to the power of a certain value, but it's empirically determined, and this is in part due to the presence of microturbulence. So microturbulence is not only present in the fusion context, it's also important for other low temperature plasmas and environments. And in the case of astrophysical shocks, so here I'll just give you the two examples that are perhaps the most striking. In astrophysical shocks, for several years it's been speculated that when you have charged particles from the solar wind interacting with the Earth's magnetosphere, you can develop certain types of small-scale oscillations. And this was well described in simulations by Mouchedi and Lambege in 2006. But it was only in 2013 where there were actual satellite measurements which identified very short-scale turbulence in the Earth's bow shock. And this was found to be due to the interaction between electrons coming in from the solar wind and ions which were reflected at the shock. So the particular case of microturbulence I'll focus on for the duration of my talk is the situation for Hall thrusters. And the idea here is that the configuration which we saw in Agnieszka's talk, for example, this E cross B configuration where we have an axial electric field and a radial magnetic field leads to the formation of this E cross B electron drift at the exit plane. And what you find is that when you have the electrons confined in this closed drift path, you can excite certain plasma waves. And in the case of Hall thrusters, as we'll see, some of these plasma waves are associated with anomalous transport, and this affects the operation of these devices. In planar magnetrons, I also been working with other colleagues who are working on deposition to show the impact of and the formation of these kinds of instabilities. So the last point I'll just mention is that in other early fusion concepts, microturbulence was also studied by a lot of authors in the 1970s. So it's a long-standing problem and studied in many different magnetized plasmas. So the Hall thruster, which you saw in section in Agnieszka's talk, looks like this. This is an image from Serge Barral, and this is the basic configuration. The axial electric field, a radial magnetic field, ions which are accelerated outside this annular ceramic cavity, an externally placed cathode, and an anode which is situated at the back of the chamber. So typically we have a magnetic field at the exit plane which is on the order of a few tens of milliteslas, and an electric field amplitude which develops to about 10 to the 4 volts per meter. So typically the drift value, the electron drift speed azimuthally is on the order of, say, 10 to the 6. So it can be extremely high. So this thruster is well known, has been used for the first thruster flew in the 1970s on the Soviet Meteor satellite. And the development of this technology owes a lot to Professor Morozov, who came up with the initial ideas, and his team worked extensively to develop the technology to where it is today. Later on, a mission actually flew with this Hall thruster. You can see this is it here. And this was an Earth to Moon mission, which was a mission intended to demonstrate that you could use plasma propulsion as the primary propulsion to fly from the Earth to the Moon. And it worked extremely well and used very little fuel, just about 80 kilograms of fuel, which is extraordinary for the distance that it flew. So plasmas of this type today are extremely important. Why? Because as you can see from this type of mission, the fuel economies you can achieve using plasmas instead of chemical propulsion are extremely important. And in many cases for long-term missions or long-duration missions, it's impossible to fly with chemical propulsion system. You would need to have a spaceship which is maybe 100% made of fuel, and even then you won't attain, it won't be enough. So plasma propulsion is interesting because it takes advantage of just ionized particles, and you can accelerate them to apply potential, accelerate them to generate thrust, and typically the mass requirements are extremely small in comparison to chemical propulsion. Today, these technologies are very widely used on board telecommunication satellites to adjust for their positioning and attitude control. And increasingly, there is a march towards what are called all-electric platforms, which are equipped only with plasma thrusters. And there are also a lot of ambitious projects recently launched, for example, just a few months ago by SpaceX and OneWeb, using satellite swarms using this technology. And in the future, we hope to develop very high thrust models, not only Hall thrusters, but also other plasma propulsion technologies. So there are a lot of challenges associated with this technology. Here I've just listed the key ones. Channel erosion, these are images from Morozov's group showing erosion of the ceramic channel due to the bombardment by high energy particles. And you also have wear of the cathode. But the chief problem today, limiting the advancement of these technologies, is the fact that it's necessary to, like for fusion devices, rely on empirical scaling. So in this case, you actually have to build the thruster and then qualify it for several millions of euros before being sure that it will operate correctly. And this is critical, you can imagine, for flight purposes. You don't want to send up on a satellite something that is not sure to operate correctly. And the reason why we have to rely on empirical scaling is, again, because of this anomalous transport. We have a very poor understanding of the high electron mobility. At the exit plane, where the electrons are meant to be confined, it turns out that the mobility is actually 100 times or 1,000 times larger than it should be. than you would expect from neoclassical mechanisms. So the question is, why? So here, I just want to underline that in the fusion case, we have to consider microturbulence in terms of how it affects confinement. In our case, the main issue here is it prevents us from producing these thrusters in a predictive, analytical way. It's necessary to develop them and at very high cost. And so we're going to look further at the role played by instabilities in this. So there are some early simulations, well, early, not so early, but some relatively recent, I guess, simulations that were performed by my colleagues at École Polytechnique. And these were 2D self-consistent simulations of the thruster plasma. And the key observation that they made, so these are 2D azimuthal axial simulations. And the key finding that they obtained in these simulations is that when you have in the normal thruster geometry, and you have this azimuthal, fast azimuthal electron drift, this is enough to excite a certain type of wave at the exit plane region. And the exit plane region is the one where we have this anomalous mobility. And what they found, so this image here is a result from their simulation showing the azimuthal direction, axial direction, and then this modulation, this field, this electric field modulation shown here. And this electric field has a wavelength on the order of 1 millimeter and below. Typically, it's associated with oscillations on the order of a few megahertz. The dispersion relation has certain properties we'll look at later. And it turns out that features are compatible with a particular type of instability that we'll look at in more detail. But for now, the image I want you to keep in mind is that instead of having a uniform plasma or electrons moving in a uniform, highly energetic donut at the exit plane, you actually have this kind of structure, this kind of a modulation of the electron density. And these are length scales on the order of 1 millimeter. So as it turns out, we'll see shortly why this particular instability is important. So these simulations showed for the first time a link between anomalous transport and a particular instability. So in the simulations, they tracked the electrostatic energy as each different modes of this instability developed as a function of time. And they found that the axial electron velocity was dramatically affected. So typically, if we have one mode, in this case, developing here, at the same time, we have a sharp increase in the axial electron velocity. Basically, electrons are supposed to be confined in this region. This mode develops, this instability develops, and then suddenly the electrons are no longer confined, so they can drift towards the anode. So this is the sign that there is some link between the appearance of this, the development of this instability, and the axial transport of electrons. So this was an important result, and is still being studied in more detail today because it's the first time that there was a clear link between, amongst all of the different types of instabilities present in the plasma thruster, evidence for one instability dictating anomalous transport. Another thing I want to mention is that when you look at the current which develops in the simulations, it turned out that this was the only effect that you needed to consider in order to calculate the exact correct value of the electron current. So it is very suggestive that this is something that we should look into further. So the question is, what experimental tools do we use? So microturbulence, in this case, we're going to be inspired by what is done in the fusion community, where a lot of, well, not a lot, but certain techniques have developed to study microturbulence. Matsukato in the 1970s used microwave scattering, which is still used. And this spectrum here is just a result from his work showing the density, electron density fluctuations as a function of length scale. And this is the kind of scaling law which he determined. And this was done in the Princeton tokamak. Now, we'll look at laser Thomson scattering. In the 80s already, there were studies in tokamaks trying to identify microturbulence signatures. And this just uses an electromagnetic radiation source across the entire plasma torus and then detection of the scattered signal. So we'll look at that shortly. And there are also a number of probe studies to study microturbulence. So as I mentioned, we'll look at laser Thomson scattering and in particular coherent Thomson scattering. And if you recall, Thomson scattering is just the scattering of an electromagnetic wave on free electrons in the plasma. And the idea here is that we can have access to different types of information according to the scales that we look at. So in the coherent Thomson scattering regime, which concerns us right now, we're going to be looking at length scales which are much larger than the electron debye length. And what that means is that we're not going to be looking at individual electron fluctuations. We're going to be looking at fluctuations which are correlated at large scale, what the electrons are doing in bulk. And the setup here is just I'll show you the experimental setup shortly, but this is just the simplest setup. We're sending in some probing beam, the laser supplied by a laser, an incident electromagnetic field, and there's some scattering which occurs in this plasma volume. And this observation wave vector is set so that we can see these correlated fluctuations. It's not just any value of wave vector. And the scattered field that we obtain here is proportional to the spatial Fourier transform of the electron density, rho. So what that means is that if we have the electrons which are dispersed completely randomly, a random soup of electrons in the plasma, we don't have a significant signal. But if we do have electrons which are bunched in a periodic, you can look at it as a sort of grating pattern, then we will get a large scattering signal if we look at those length scales. And the way to see it is pretty much that. You can see this type of bunching when you have waves present in the plasma. And this is the property we'll try to exploit in terms of detecting whether we have a wave at the predicted millimeter scale wavelength. So this has been done in fusion plasmas. Can we do it for the Hall thruster? And this is a reminder of what we have, we're going up against. We're trying to detect millimeter and submillimeter scales, wavelength for this instability, megahertz frequencies. So this already means that other diagnostics are not well suited to this type of investigation. If we want to, say, try to look at probes, we don't have probe responses which are sufficiently fast to capture this kind of behavior. We also have probes which are much larger than the scales we want to look at. So we have to use this optical technique. We are basically forced to consider a fusion diagnostic in low temperature plasmas because of this complex physics. The other issue here is that we're using an optical diagnostic, we're using a scattering diagnostic, and the challenge here in comparison to fusion plasmas is that we have densities which are much lower. So the challenge here is that will we get a strong enough signal to detect this type of fluctuation? So, this work, the diagnostic is known as Praxis. So, sorry about the acronym. I thought it was a good name at the time, but I realized it was quite limiting. This is the diagnostic shown here. It's in the optical bench using a CO2 laser, 40 watt, 10.6 micron continuous laser. And the idea here, this is our radiation source. We're operating in the infrared. And we're going to send our radiation source across our plasma and collect the scattered signal and send it to a detector on the bench. So we have also infrared detector, HGCDTE. So I'll show the details on the next slides. But basically, this is we have, for investigations on the thruster, we have a setup where the optical bench is set up beside the vacuum vessel. We have access ports on the side of the vessel. And the thruster, which is typically in the kilowatt range, is located on the axis of the device. So we can traverse the plasma and then through a set of windows, recover the scattered signal, and then using a lot of mirrors, send the scattered signal across. It's actually sent here. This line is actually under the vessel and across to other mirrors and then back to a detector. So it's an optical path which is several meters and quite dangerous because it's infrared. So yeah, you have to avoid just going into the laser. But it's necessary for what we want to do. This high power is required to get enough of a scattered signal in our low density plasma. So this is just a view of the top of the bench, showing the laser, a shaping element, a ceramic tube here, and then the splitting of this initial beam into two components, one frequency shifted local oscillator, which we'll see shortly, and then the main primary beam. So the point of this, all of the optics on the bench here, which might be difficult to follow, are set up so that we can fix our observation length scales as we want. So we can change the length scale that we're looking at. We can also change the orientation, try to understand in which directions is the instability propagating. So all of the elements here are designed to achieve that goal. So this will be clearer on this slide, where this is the basic setup. Local oscillator, as I mentioned, which is going to interfere with the fluctuating field of interest. The primary beam, which is most of the 40 watts, and this serves as the intense radiation source which we're using for scattering. And the combined beams here intersect in front of the thruster, and this is the observation volume, which is defined by their intersection. And this is the observation wave vector, K. And as you can see from this setup here, what we can do is change the angle, theta, between the beams, and that automatically changes the length scale that we are looking at. But at the same time, we can also change the plane in which this particular wave vector is situated. So it means we can have a sort of a map in different directions in space to determine, is there a privileged direction in which this instability propagates. So here I just, again, there are many steps involved, but I just want to summarize the very basic ones. We have a time-varying complex signal. We perform the FFT, and we have an arbitrary signal here, typically two symmetric peaks corresponding to the two channels we observe. And then using parameters from the experiment, such as the laser power, beam waste, etc., we can obtain an actual a spectrum which is a reflection of the intensity of density fluctuations. It's a real value. It's no longer arbitrary, and this is a calibration that we perform using our experimental parameters. And then if we integrate the spectrum, we can obtain what is known as a static form factor. Again, a reflection of the intensity of these density fluctuations, how much energy is contained in these oscillations. So this is just an example of a signal spectrum. For people working on fusion and who worked on coherent scattering, this S of K, this dynamic form factor, and the static form factor, which is just a value, they are familiar with it. When I showed the figure from Matsukato's work from the 70s, he was using these same form factors and dynamic form factors to basically plot these scaling laws. So this is the same thing we're doing here. So here I just want to show a few excerpts from our work, and the key one is that we're able to detect this instability, which is known as the electron cyclotron drift instability, at the predicted frequencies and wave numbers from the simulations. So the frequencies are on the order of a few megahertz. The wave number here corresponds to length scales on between about 0.5 and 2 millimeters. That's typically the range we explored. But that is exactly these are the length scales that were predicted to be important for this instability, and we found them experimentally. Over the same length scale, we can again plot some energy scaling law, and it turns out this is a log to the base 10 of the density fluctuation intensity, and you see here it's dropping off exponentially. So from this slide, this is the key result, which shows that it is possible to find this particular instability as predicted from the simulations. It's a fundamental instability driven. The source of free energy is just the very fast azimuthal electron drift. In the same direction, we have ions which have a velocity which is pretty much zero. And this sets up a charge separation, and we can excite this small scale wave. So from this result, this was interesting finding. We have the frequencies expected, we have the length scales expected. Another result is understanding how the mode propagates in space. So in the initial models that were considered, both linear kinetic theory and also in the simulations that were run, this instability was speculated to propagate either in 1D, so primarily in the azimuthal direction, or 2D, in the azimuthal and axial directions. And experimentally, we were able to show that the instability actually propagates in 3 dimensions. It has a small component which is along the magnetic field, and this was quite unexpected. But this result, it might be a bit difficult to follow, but this is the azimuthal direction, so the E cross B drift. This is the E direction, this is B. And instead of propagating in this direction, this instability actually, it's in three dimensions. So this is what I've shown here, this main propagation direction determined experimentally. So this result had some impact, which we will see shortly. When we consider, when we take into account the actual experimental measurement, we've determined that not only is this instability present, but its propagation is more complex than what the initial models predicted. Once we take that into account, we have to look at, instead of the 2D linear kinetic theory solution or the 1D, we now have to look at the 3D case. And when we do this, so these are solutions of this linear kinetic theory, taking into account the propagation of the mode in 3 dimensions. Here I've shown the azimuthal wave number as a function of the axial wave number, and this is the frequency. So the frequency, this is a megahertz. So, you know, this is 9 megahertz up here, and then the blue is on the order of 1 megahertz. So this frequency, what I've shown here is a continuous. There are no gaps, no unstable lobes and stable lobes. Everything, the mode is always excited, whatever the value of wave number that you use. And here, if we fix, for example, we set our kx to 0, and we just look at how the frequency varies in one direction, say along ky. What we find is this linear variation frequency, this megahertz, and then the length scale in radians per meter. And what we find here is a linear slope. And the value, this group velocity of the instability, is exactly what we measure in experiments. So I guess the takeaway to get from this slide after all I presented is that initially from theory, simulations that were considered a very simple mode. Experiments show something a lot more complex. And once we move our theory forward to take into account some of these effects, then everything matches up. The theory matches up perfectly with the experiments. So this was a satisfying finding. And I won't go into detail of the other, all of the other things we found, but there was further analysis of this 3D dispersion relation, which was performed by Cavalier and us. And my colleagues also worked on simulations studying the effect of this 3D propagation. Is there a possibility that this instability also contributes to radial heating of electrons? So this was studied recently. And we also identified a new instability due to the presence of 2 types of ions in the axial direction. And then here we also, with colleagues in Orsay, identified this type of instability in planar magnetrons. And now we also have done some plasma wall interaction studies. But overall, we got a lot of information from the application of coherent Thompson scattering. Again, it's not the first choice diagnostic. If you want to study features of your low temperature plasma, it seems like we're taking a huge complex tool to study a very specific thing. But this is basically we were forced to do it because no other diagnostic could give us information about this microturbulence. So in spite of what I presented, you should know there's still a lot of stuff missing. And the question is, these are some of the questions that we can continue to ask. What is this wave particle interaction between the instability we found? Can we measure this fluctuating field? And what are the other instabilities that might be involved in anomalous transport? And sorry about the gap. So here I just want to mention that based on this work and the work by Aaron, Adam, and Laval in 2004, now there are about 10 research groups around the world who are working on this particular aspect of microturbulence. And so can we also try instability control? So I'll return to this point later. But for now, the strategy in the next part of this talk is to look at other advanced diagnostics, to try to see if we can, by using complementary tools, get some answers to some of these questions that I'm asking here. So for this, now we move to the incoherent Thompson scattering development effort. And the idea here is, before we were looking at the correlated electron density fluctuations. And now we're going to be looking at locally the electron temperature and density, and hopefully drift velocity as well. And so we're going to be looking at the incoherent regime, where our investigating length scale, the scattering length scale, is smaller than the electron Debye length. So we have the same challenge as for the coherent Thompson scattering case. We're dealing with a very low density plasma compared to fusion, even though we're stealing a fusion tool. And these are some of the requirements. We want to try to look at electron temperatures covering a wide range, and to also study deviations, possible deviations from Maxwellian behavior, which are seen in simulations. So it's very difficult to do, but hopefully it'll work. So this diagnostic effort, I want to acknowledge my collaborators here who made the funding of this new diagnostic possible. And these are people in Orsay, planar magnetrons. the French Atomic Energy Commission, who are interested in using it for their, studying their plasma stage in their ECR source, and also the French Space Agency, which is interested in using it for thrusters. So all of these people, these partners, made it possible to fund this diagnostic development from 2016. So this is the diagnostic design. Again, sorry, more acronyms, but I thought this would be a cool one. This is the name of the diagnostic, and this is the setup shown here. This time we're using a 532 nanometer, so a visible laser, a pulsed laser, Nd:YAG, and these are the properties here. So the laser is set up as shown on the bench here. We have a beam expander to expand the beam from the initial diameter of 9 millimeters to 27 millimeters, and then we have a periscope and a lens, and we're focusing our probing beam into the plasma shown here. And we're sending it across these arms, these long arms, which are supposed to basically equipped with Brewster windows, which basically prevent us from capturing in our observation volume region the stray light reflections from the windows. So here we have a beam dump, and perpendicular to this line, we have our fiber, optical fiber, which is going to be collecting the scattered photons from our plasma volume, and then sending these transmitting these scattered photons to these elements. So our diagnostic is different from the classical Thomson scattering diagnostic in a few aspects. But the key aspect here is that instead of sending our scattered radiation to a triple grating spectrometer, which is, if you've seen a triple grating spectrometer, is a pretty sizable device, we're sending it across a single spectrometer and a special kind of notch filter, which was only commercialized about 10 years ago by the company Optigrate. And what this does is that it significantly reduces the transmission losses. Again, we're dealing with a very low density plasma, and we have few scattered photons that we're trying to collect. But if we pass this in a triple grating spectrometer, the transmission, due to losses at the windows, at the multiple mirrors, the transmission can be quite low. In our case, we have a single spectrometer, and this optical element, which I've called the BNF, a Bragg notch filter, which has a transmission of 90%, a transmission of 90%. So these elements put together means that the transmission efficiency is extremely high, and we're able to, hopefully, capture most of the photons that are scattered from our volume. So this is the key, this is the trick, I guess you would say. So we did first design validation on a hollow cathode discharge, and the setup is shown here. So this is the hollow cathode. The choice of the hollow cathode was to basically do measurements, validate the diagnostic design by proving that it's possible to measure in a low density test plasma. So this is the test plasma. And so the setup, the signal procedures are completely different from for the coherent scattering case. We have a scattered spectrum, a raw scattered spectrum, which contains our Thompson signal here, a stray light signal, and plasma emission peaks. So we can have some background acquisitions which you can subtract from this and then obtain something which is relatively clean. So typically in amplitude, it's in counts, photon counts, and as a function of wavelength. And with appropriate calibration, we can actually transform this spectrum from something which is just an arbitrary, nice spectral shape to something which means something. So the area here is no longer in counts and wavelength. We can actually calibrate it so we can get electron density out from this, proportional to this area. And the Gaussian, the spectral width is also proportional to the square root of the electron temperature if we have a Maxwellian distribution for the electron velocities. And the derivative, we can of course obtain the EEDF. So using these procedures can give us a spectrum from which we can get the local electron properties, which is what we are seeking. So the setup here in the plasma is actually, I've shown a schematic view for the cathode plasma, and we have the laser beam sent in, the detection direction shown here, and our observation wave vector is here. So typically the observation volume, the scattering volume that we're collecting information from is only on the order of about a cubic millimeter in volume. So this slide, I just want to prove to you that we have been able to validate the diagnostic on a hollow cathode, and these are the results. Nice spectrum. This area here is the filter region, which we exclude. And we're able to measure density on the order of 10 to 16, which is 10 to 16 per cubic meter, which is unprecedented, I guess. And it shows the sensitivity of the diagnostic. So you can see here, this is just 2 counts. We're basically able to resolve a very weak signal and very low densities. So this is validation of the design choices, and particularly the use of the single monochromator and the new Bragg notch filter. So this is the setup for thruster studies shown here, and the advantage here is that the selectivity that we have with Thomson scattering diagnostics in general allows us to fix our direction of observation. And so this means that if we are in this configuration here, for example, then we can measure electron properties along this direction k, and this measurement corresponds to the azimuthal electron temperature, velocity, and drift. And in another scenario, if we have, so here I've shown actually this k, so depending on where you place it, it's not, these figures aren't very clear, I guess. But in this case, the k would be pointing along the same direction as the radial version here, the radial direction here. So this would be the radial electron temperature. And in this case here, on the other side, this would correspond to the azimuthal temperature measurement. So just by shifting where which part of the plasma you look at, you can access radial information and azimuthal information. So this is why this is the setup here. So this is just an example before moving on to the next point. But we have access for the first time to reliable electron temperature measurements in thrusters. And this is a magnetically shielded thruster operated with krypton. And just an example I wanted to show here where we have the electron temperature, which is extremely high at the exit plane, but it's reasonable, and dropping off to a few eV some distance away, and then electron density, which is actually on the order of 10 to 16, and then dropping off as shown here. So these are some early measurements, and now we have a paper which is in print, but not in print, submitted, showing, comparing measurements on a magnetically shielded thruster and a standard thruster. So I'll end with some strategies to exploit this data, take this data further. So, okay, so I don't want to offend the people working on fusion, but the idea here is to try to look for some similarity between wave particle interaction in our case and what happens in fusion. And to do so, we look at a particular case established by Carney, ion heating by a lower hybrid wave. And he established a resonance condition. Basically, if you have the instantaneous velocity of the particle and multiplied by the wave number is equal to the wave phase velocity, then you can have strong interaction between the wave and the particle, which is undergoing its orbit around the magnetic field line. So it's a very particular resonance condition which was considered by Alexander de Croo for the Hall thruster case in 2006. And the question is, can we actually meet this resonance condition and explain why we have energy transfer between this cyclotron drift instability and electrons? So we are applying this analogy to our case. The idea is actually, now that we have this information from experiments, we can hope to do so, because all of these parameters are parameters which we now have from experiments. So omega d is the wave frequency in the electron frame. So this is the frequency that we measure in experiments. This is the wave number that we have in experiments. And the drift velocity is what we can measure from incoherent Thompson scattering, incoherent Thompson scattering setup. Now, the criterion for transfer of energy from the wave to the electrons is basically for the ACDI wave frequency in the electron frame to be greater than the electron cyclotron frequency. This is the criterion. And once this is satisfied, then we can have potentially energy transfer. So we have a very simple form. We can check if this is justified. And it turns out that yes, this is actually a condition which is met in our experiments. We can also estimate the fluctuating field, which I mentioned before, because now we have the fluctuating, the density fluctuation from CTS, incoherent Thompson scattering, the density, and also these parameters, TE, the electron temperature from incoherent Thompson scattering. So we can get a better estimate of the fluctuating field. And then we have other investigations we can do using Ducrot's formulae, where we can determine this, if the stochasticity threshold for transport is satisfied. So we have our fluctuating field, which should be a third of the actual applied field, and this can be satisfied. And also we can determine an axial electron velocity. When the electrons, when there's interaction between this wave and the electrons, which are supposed to be trapped, there's a certain axial velocity which you can get out. And this is actually something we can calculate now. So I just want to give an overview and show that these are simple models, but having access to extremely difficult to obtain data on the electrons can actually make it possible to advance a bit in our understanding of transport, not only by the instability I've presented, but also by other waves. So other waves, I will soon have to end, but how much time do I have? 4 minutes. Okay, so here I just wanted to mention that I presented this short scale instability, but there are other ideas, particularly at large scale behavior, which other colleagues have put forward, basically saying the transport is not necessarily dominated by these scales, but by this large scale plasma in a non-uniformity. So this is something that is still being looked at by our colleagues and us. But now we have access to electron properties, we can try to determine information on, for example, there are basic criteria for example, if it's an ion acoustic mode, is there an ion acoustic mode which is present? So we have to look at, for example, the ratio of TE over TI, also study gradients, and we can also measure the drift of electrons, so this is important information. So to end, I'd like to say, sorry if this presentation was a bit maybe offensive for the fusion people and maybe offensive for the low temperature plasma people, but the idea here is that advanced diagnostics like this can give us important information on microturbulence, and it is important not only for fusion devices but also for low temperature plasmas as well. And we can complement these studies, so my strategy is to use another diagnostic, incoherent Thompson scattering, to better understand the information we get out on these plasma fluctuations. And this will give us ways to study anomalous transport, to study different types of instabilities, and to understand whether it's even feasible to expect certain types of modes to be excited in the plasma. So this information we can exploit directly. And there are other studies that I'm working on other topics related to these instabilities. So I'd like to acknowledge my colleagues. This is the fruit of work by many groups and many colleagues. So this is my former PhD advisor, and these are my colleagues who did simulations and other experimental work, and then my current colleagues at ICAR, and my colleagues on other sources, and of course, my student who's now working on incoherent Thompson scattering. So thanks for your attention, and yes.
Thank you very much for this comprehensive talk on Thompson scattering. Any questions from the, please?
Yes, so I wanted to ask, what were the conditions at which the thruster was operated? Did you observe these electron drift instabilities at all conditions, or did you choose some specific?
No, you don't have to choose any specific condition if you're operating a small thruster or a large thruster for the range of operating voltages, which is typical between, say, 100 to, say, 800 volts on a large thruster. You will find this mode, because basically the only thing that's driving it is the azimuthal electron drift. And you have this in any type of thruster. It's not an instability specific to a particular gradient or a particular electron temperature. It's always present. And the driver is the fast 10 to the 6, between 10 to the 6 and 10 to the 5 meters per second drift, which is in all thrusters. So this is why it's a fundamental instability. Yeah.
Other questions? Jacek?
Okay, thank you. Yes, please. Can you correlate anomalous erosion and drifting stability with your method?
Yeah. Okay, erosion. The difficulty is erosion. To study it properly, you would need.
You showed something about it at the first slide or the second slide. I don't remember exactly.
Yes. Okay, so yeah, this is a good question. So in fact, yes, where is it?
Oh, yes, but yes, here it
so
is.
In fact, the periodicity of these striations corresponds. It's the same wavelength as this azimuthal instability. So what we propose is that maybe there's a standing wave that is set up, a standing wave pattern, which enables these trenches to be dug in the wall. But the problem is the instability it's propagating. So normally you'd expect it to be something smooth. You'd expect the fluctuations, density fluctuations are not really expected to be locked into one place. You would need that condition to justify why you have these grooves which are fixed and not just smoothed eventually. So we've done calculations to show that there might be some reflection of the mode which you can set up. There are conditions where you can set up a standing wave, but for now it's not conclusive. We have to do more measurements. So this would be something to investigate further. But we have put forth and published a hypothesis that erosion is linked to this small scale azimuthal mode. Yeah. But it's not 100%.
Okay.
Justified. Okay. It's not categorically, it's not 100% sure, but yeah. It's suggestive, yeah, the fact that we have this millimeter scale, pattern.
Okay, thank you very much.
Yeah, thank you.
Any other questions? I didn't see, so let's thank the speaker again.